Okay, thank you very much for the invitation. And well, this kind of meeting are very dangerous. Because 1 year ago, I was invited also at TNG, and I was sitting as a listener. And you see, 1 year later, you sit in front of the audience. So it's dangerous. Be careful. Right. So yes, I'm Loïc. I'm very happy to be here. I'm a French guy. I'm now living for about 28 years in Germany. And well, that's when I started my professional career in software development and designing software, software systems, so very strong on the implementation side of things. First doing 11 years in more the server market, high performance computing, telecom, air traffic control, airline IT, and then moving in 2007 to the embedded medical device, automotive, and since 2018 I'm now technical trainer at Doulos. Doulos is a training company which delivers great training in hardware design and verification, but also in embedded and in Python, AGI, and machine learning. And our mission is not only that the participant enjoy the training, learning new technology, but also that the participant get project ready quickly. And why I'm talking here? Because I'm developing right now a new training called Zephyr Essentials. And what I did, I just took some slides from the training that I'm presenting now. So let's talk about embedded product development. Who has already done embedded product development? Let me know. Oh, okay, cool. Who has already worked with Zephyr? Okay, I see, okay. So, well, as you know, in theory, assuming a V model, we first start with some product requirement. Then what happens, we select a processor, an SoC, a system on chip, a board, perhaps an operating system. At that point, the team split. We do software development, hardware development in parallel. And then we come together. There may be some bug to fix, test and validation, and you iterate as needed. Does that work that way? Have you seen that? Well, I never have seen that working. In practice, what happens is you start already working on the product requirements are not finished. Don't tell that to your auditor if you have some audit. Then what happens is about the software development, you have selected the processor or board, but what about the board support package? We need to port perhaps the operating system to the board you have selected. What about the driver? What about the software stack? If you do communication, TCP, IP, Bluetooth, what have you? And these are all valid questions. Of course, if you have certain experience, that things you will clarify up front, but sometimes you just discover as you go. You don't know what you don't know. And also, when you do hardware development, what can happen is that your hardware colleague come and say, oh yeah, I have just integrated the GSM module, could you test it? No, I don't have any driver, sorry, I cannot just test it. Also, what happened with the hardware bring up, normally that's something that should be easy, but depending, I've heard a story that it takes sometimes months to get that working. There is a big semiconductor in Munich. They do a so-called boot camp. They send all the company, all the working site on the project in Nuremberg on Friday, and the job on Monday, the board should be up and running. 84-hour non-stop jobs. Anyway, what will happen also is that you will have change in your project, not only because the customer is working with a product, but also you gain experience, things you thought that would work like that does not work like that. And also there is a time budget constraint that will change the perhaps amount of feature you will deliver because you are late. That's reality. So now the question is, how Zephyr can help us with this picture? Yes, but for that, things like agile methodology, continuous integration, continuous development. There are atoms to mitigate this issue with some various degrees of success, to put it diplomatically. Okay, so now let's see how Zephyr can help us with what we have just seen. I don't want to repeat what Kate just mentioned. All the common architecture we have an embedded product are supported. Hundreds of boards are also supported. So it means for us likely less BSP work. So that's a good news already. Also, if you look at the Zephyr project, yeah, that's what you get if you follow the Getting Started guide. If you look at Zephyr drivers, you see a lot of drivers, as Kate already mentioned. I did some heuristic. I found there are about 950 different peripherals supported. I don't know how good my heuristic is, but that's what I found. I can show you how you can find this number. Also, from a feature point of view, we not only have, I would say, the classical services that an embedded OS will offer, like starting thread, managing, exchanging messages, managing interrupt service routine. But we have seen we have a lot of drivers. There are a lot of high-level services like logging, file system, sensor, sensing system. That's a framework that allows you to do sensor fusion. It's it's available. You can use it. And then we have all the communication stack, TCP/IP, Bluetooth Low Energy, Wi-Fi, NFC, plus some other like Thread, Matter. And from the application, high-level application services, here we see the classical protocol we have for embedded device, for IoT device, like MQTT, COAP, and AWM2M. So now we see we have all these features, and we have seen that Zephyr runs on all kinds of boards. So how do we now make that available? We couldn't enable everything. We get a big image of a few gigabytes. That would be one option that does not work in embedded. So of course, what we would like to do is, well, I have my target, my application, and I need to select some of these features I want to enable. And the way you do this pickup is with kconfig. Kconfig is simply you have this box, this toolbox of Lego, and then you pick up the Lego you need for your product. If you are coming from embedded Linux or from Linux, that's something that will look familiar to you, but the way we use kconfig in Zephyr is slightly different. There is a joke in the Zephyr community that says that Zephyr is 80% configuration and 20% coding. There's some kind of truth to that. It means we don't have to develop ourselves. Instead, we can reuse what's there. It's just a matter of knowing how to enable it. Another aspect how Zephyr managed to be portable across all these varieties of hardware is through device tree. Device tree is simply a syntax, a language that describes the hardware, the information about the hardware, and how you want to configure the hardware at boot time. So there are some information, you see that on the schematic, and you need to give that to the operating system so that it knows, oh, if I talk to this device, and which address should I talk to? If you are coming again from embedded Linux, that's something you know, but here there is a big, big difference. We don't have a device tree blob, which is a binary file. Instead, what we have in Zephyr is an header file. So the device resource and the binding, when you call West build, it will generate an header that you can then use in your code. And all this device tree and the query of the information happen through macro, through C macro. And this is where if you have a mistake, suddenly you can have very easily hundreds of compilers error because of that. So now you may say, okay, if we think about what we just say, how does it help when we develop product? And the way you develop an embedded product with Zephyr is a completely different mindset. What I do, instead of perhaps starting, yeah, I will need this driver, and going from bottom up, we do exactly the other way around. So first of all, what we can do is, because it supports many boards and peripherals, and because the software can be ported quickly, what you can do is, hey, first validate your idea. We have seen we need to select the processor and the boards. What you can do, hey, you take the boards that are out of there, and you can already try and play and see what fits your build. Also, what you can do, and there will be a talk about that, is you can start developing your software. Let's say here you want to support this device here. Maybe this is already supported by Zephyr. Maybe you have to develop the corresponding driver. What you can do is you can already develop the driver for this device and use the native simulator without any hardware and already validate your driver. And that's quite powerful, and I'm very excited about the talk that comes after the break. And as I just mentioned, in other embedded OS, what we do, it invites to take a bottom-up approach. You don't have to take this approach, but it will invite you to do so. Whereas in Zephyr, we really think about the functional block diagram, and it's about to see, okay, I will need this function, this block, like Lego building blocks. So now, there is a valid question that we should ask, and challenges perhaps related to what we have just discussed. First of all, well, supporting multiple hardware, is that perhaps an overkill? Because, when you have embedded, well, you have only one hardware and that's it. And also, all this abstraction and all this, doesn't it perhaps come with some performance penalties? So here, what the Zephyr community decided is we don't want to compromise. Zephyr can run on super big IRAM and on super small microcontroller. So how you achieve that? This modularity we have seen is through kconfig, and everything should happen at compile time. So now, there are many things you should take care of, and the Zephyr project will abstract you some of the groundwork from you away. But in order to take advantage of Zephyr, what will happen is there are many pieces we need to work with and you will encounter. I don't know how was your first time with Zephyr. The getting started way was great, but then I wanted to integrate a device I had on my desk, and 3 weeks was a nightmare for me. I don't know about you, but that's what happened to me at least. Okay, and there are many things we need to, and many ways we need to understand to really appreciate and enjoy Zephyr. And one of them is West, then we have CMake, Ninja, CMakelist.txt, project.conf, pristine build, overlays, kconfig, device sweep, DT binding, YAML, macrobatics, manifest, workspace, and I'm sure I'm forgetting a few more, sysbuild. And okay, that's the price to pay. Once we don't have to master everything in one go, but we need to have a certain understanding of how the system works to really appreciate. What happened once I got an understanding, I could take all the devices that we do in our driver class, that we are using on our driver class in a half day. And for me, that was a kind of revelation. Okay, what else? Yes. So why use Zephyr? We have a wide support for hardware peripheral software stack. We can abstract, with abstraction layer, we can mitigate hardware migration costs. That will become more and more important to increase resiliency. First of all, we have seen during COVID, there is something like supply chain disruptions. But also you could, for products that have a long lifetime span, like 10 years, you could have also end of life for the processor, which is a drama normally. So here what you do, you can save time and money with Zephyr. Also, we have seen device with constrained resource. We achieve that through modular compile time approach. And what Kate mentioned, security. This is Zephyr is built with security in mind. And I'm also very excited about the safety talk that come after this presentation. And finally, the licensing foster collaborations, but also allow competitions. And yeah, so that's things where I say there is something very interesting here, and that's why also my company decided to invest time and money for me to play with Zephyr and create a great training. I just want to close, 5 minutes left, perfect. I have a small demo prepared that I want to show you. Let's see if that works. Let's play this one. So I don't know how I bring that to, yeah. So here what I have a stupid hello world. So you see it's not really super exciting right now. But what I can do, I can compile for different boards. The NRF52, the MCX 947. You have these two boards on the desk. And so here I'm compiling first for the MCX. And then I will flash. I will try to remove this. Oh. Well, I'm very sorry. I can't remove the things. Okay, anyway. Okay, now we have compiled. I can start the connections. I reset the board. Okay, hello world. It's not very exciting, but with this hello world, I will show you how you can take a device into operation even if you don't have the driver for it. Just as a proof of concept, I think the next things I do, I recompile this for another boards using a pristine build. Yeah, for the NRF. And check. Okay, now you see that's the compile time I just mentioned. And then now what I will do, I will, yeah, that's the board I have. I have the MCX 947, and I would like to take this device into operation. That's an RGB display with backlight, an LCD display. Actually, there is the driver for it in Zephyr. But assuming I wouldn't have the driver. So here what I do in my project.conf, I enable some configuration, the shell and I2C shell. That's this Lego building block you can enable. And I will just recompile for the board. So now the image is bigger. Before it was 20 kilobytes, now it's 52. All right, so now I'm flashing. And when I connect to the serial console, what I see, I reboot the board. I will see I have the LTS, that's my board, but now I see this UART. So that's an interactive shell I just enabled with the config. And then I just go to this serial console again using Minicom so that it's a bit bigger to see. And what you see, you have here the we have the interactive shell with some command we can use. I will demonstrate if you want, and we are almost done. 30 seconds left on my timer. Yes, so here you have the I2C command. We have here, we can see list the device. We can also, with kernel, check some configuration. That's something that is really great during development. For example, with, okay, that's 3.7. Here you could see the thread running on your system. Here we have 3 threads, the schedule out, and these 2 system threads, the syswork queue and idle. And with kernel stack, I can see also the current stack. We don't see, unfortunately, it's there. And then what I do an I2C scan. So I scan the I2C bus. So here, no software from me. I'm just using what's there. Okay, I need to give the I2C controller. So here I'm doing that on the MCX platform, but you could do that on the NRF. That will work exactly the same. So here we have the device on the I2C bus at 3 and 6.2. 3, that's for the LCD, and 6.2, that's for the backplane. And here I just look at the data sheet, or you look at some example how you could send bytes in order to just take this device into operation. So here with these 3 bytes you are sending on register 0, 1, and 8, you initialize the device. And then if I send the value on register 4, that's for red, 3, that's for green, and 2, that's for blue. So here, full red. So you see so you can take your device into operation even if you don't have any software, just with an hello world. And thank you very much for your attendees. I hope you enjoy it.